Okay, so what if you could take a piece of the sun, something powerful enough to bend radio waves clean across the solar system, and literally put it in a jar? It sounds like total science fiction, I know, but today we're actually going to walk through the real world blueprint for how scientists are doing pretty much that. We're building a sun in a jar.
It all kicks off with this wild observation. Out in space, these massive solar flares. We're talking huge explosions of superheated gas. They're so powerful, they can act like these giant cosmic lenses, actually bending radio signals. So naturally, this got scientists thinking, what if we could harness that same physics and build a tiny version right here on Earth?
So, to build our own, we first have to understand the original, right? The sun, it's not just a big ball of fire, it's this colossal physics engine. And when it erupts, its flares can be like natural amplifiers. They can boost radio waves or even stamp unique signatures on them, almost like a cosmic watermark.
The core concept here is called plasma lensing, and it's a perfect name for it. Just think of a camera lens, right? But instead of glass, it's made of that superheated gas, plasma. And instead of a machine carefully grinding it into shape, the sun's incredibly powerful magnetic fields do all the sculpting. This plasma lens bends radio waves just like a glass lens bends light. It's that simple. So if we want to build one, we have to be realistic. I mean, it is one thing to demonstrate the physics in a nice, controlled lab environment, but it's a whole other ballgame to try and match the scale of the sun itself. So let's just put these two side by side for a second.
I mean, the difference in scale is it's absolutely mind-boggling. In the lab, everything's under control, we can repeat our experiments. A real solar flare, that's pure, unpredictable chaos. Our machine, it might be the size of a room. A flare can be bigger than a planet. We're talking about feasible engineering versus something that is straight-up science fiction. The power gap alone is just staggering.
And this gets to the absolute crucial point, which the source material puts perfectly. The goal isn't to build a machine to control the sun. That is not the point at all. The goal is to build a valid analog, a perfect little scale model that lets us study the fundamental physics up close in a controlled way that would be totally impossible otherwise.
Okay, so how do you actually build one? Let's get into the blueprint. Honestly, the best way to think about it is like a recipe, with 3 main ingredients you need to cook up this miniature cosmic lens. Ingredient number 1 is the heart of the machine, the plasma source. This is where the magic happens. This is where we literally create our sun in a jar. It's usually a device called a helicon source, and what it does is it blasts radio waves into a tube of gas that's sitting inside a vacuum, heating it up until, poof, it ignites into a stable, glowing column of plasma. And here's your shopping list. You're going to need a special quartz or glass tube that can handle extreme heat, a little puff of a gas like argon, some very carefully wound copper antennas to shoot the radio waves in, and of course, a really powerful RF generator to give it all the juice. All right, once you've got your plasma glowing, you need to shape it. And that's ingredient number 2, the magnetic sculptors. These are powerful, water-cooled copper coils that generate these incredibly precise magnetic fields. They basically act like invisible hands, molding and sculpting that column of plasma into the exact lens shape the scientists need for whatever experiment they're running. And finally, ingredient number 3. Because what good is a lens if you have nothing to shine through it? That's where the signal injector comes in. It's this really sophisticated system that can generate pretty much any radio signal you can imagine, fire it right through the plasma, and then, this is the important part, precisely measure what comes out the other side. But here's the secret sauce that really brings it all together. See, these parts can't just run on their own. Everything has to be perfectly synchronized, down to the microsecond. And that's the job of a special computer chip, an FPGA, which acts like the machine's central nervous system, conducting this whole orchestra of physics. So, we have the blueprint, we've put the machine together, now for the fun part. What can you actually do with a lab-scale plasma lens? Let's check out the payoff. Well, the whole point is to run experiments that make these really complex theories tangible. And one of the coolest proofs of concept is something that sounds like it's straight out of a spy movie, creating a vanishing antenna. So check this out. Here's how it works. First, you fire up the plasma column. Then, you inject a radio signal into it. Now, because that glowing plasma is conductive, the column itself becomes the antenna, broadcasting the signal out. But then, and this is the amazing part, the second you cut the power, the plasma just disappears. The antenna is gone. Instantly.
It's a fully reconfigurable antenna that you can switch on and off whenever you want.
Now, this kind of cutting-edge research is obviously incredible, but it doesn't happen for free. So let's get down to the bottom line and talk about what it actually costs to build one of these machines.
So let's just get right to it. If you wanted to set up your own lab and start bending radio waves with plasma, what kind of budget are you actually looking at? For a solid university-level lab using all new components, you're looking at a price tag somewhere in the ballpark of $75,000 to $200,000. It's a serious investment, for sure, but maybe a little more accessible than you'd think for this level of fundamental physics.
And that money goes to some seriously specialized gear. I mean, the vacuum system alone can set you back over $20,000. The RF generator and the power supplies, those are also big-ticket items. But the real kicker for a lot of people is the diagnostics. The equipment you need just to measure the results can easily be the most expensive part of the entire setup.
And this really is the takeaway, isn't it? To push the boundaries of what we know, to explore the rules that govern everything from a solar flare to the signal in your phone. It's not enough to just have brilliant ideas. It requires a serious, significant investment in the people and the technology to make those ideas a reality.
Which leaves us with one final fascinating thought. We now know how to put a tiny piece of the sun in a jar so we can study it. So it really makes you wonder, if we can bottle a solar flare today, what other cosmic secrets are we going to unlock next?